Clicking Run on a piece of software feels instantaneous, but beneath the surface of your screen, that click triggers a massive, high-speed mechanical operation. Take a look at this 3-layer hierarchy chart. At the top is a standard line of math you might type into a program, x equals x plus 1. To map out what the hardware is actually doing, we have to translate that down into an assembly language. Now our single line of code is broken into 3 distinct commands: load a value, add 1 to it, and store the result. But the processor cannot read those English commands. It only understands raw binary. Notice how this bottom string of 1s and 0s splits perfectly down the middle. The left half is the opcode, which tells the hardware what action to take. The right half is the operand, which tells it exactly where to find the target data. Every piece of software ever written, from a simple script to a modern video game, has to be translated into this exact binary structure. It is the only way to bridge the gap between human intent and physical hardware. To understand how computation actually happens, we have to look at physical reality. Early engineers built massive, room-sized racks of wiring just to execute basic logic. Today, those giant racks have been miniaturized into microscopic silicon, like this MOS 6502 microprocessor. But the architecture remains largely the same. The CPU acts as the active brain, while the RAM sits completely separate as a storage vault. This split-screen diagram shows us exactly how they interact. Inside the CPU, we have short-term memory slots called registers. The program counter tracks our place in the code. The memory address register points to specific locations in RAM. The memory data register holds the information moving back and forth. The current instruction register holds the command we are actively working on. And the accumulator is our scratchpad for doing math. The execution cycle always begins with the fetch stage. The program counter knows which instruction is up next. It takes that address and pushes it across a one-way path, the address bus, straight into the memory address register, which points to a specific slot in the RAM grid. Once the RAM locates that specific address, the data makes the return trip. It flows back along a two-way street called the data bus, lands in the memory data register, and finally drops down into the current instruction register. There is a counter and turn and timing quirk here. Before the CPU even attempts to read the instruction it just fetched, the program counter immediately ticks up by 1. It is already preparing for the next cycle. The entire fetch stage is simply a logistical hurdle. It is the physical process of moving electrical signals across the void between RAM and the CPU, so the actual work can begin. Now we enter the decode stage. The control unit acts like a switchboard operator. It cracks open the current instruction register to look at the binary. It separates the opcode from the operand, figuring out exactly which physical wires need to receive power. In this case, we are executing a load command. The operand is an address, which means we have to go back out to memory. We slide that address into the memory address register, pull the target data from RAM into the memory data register, and drop it into our accumulator workspace. Let's test your mental model. The CPU now needs to fetch the next instruction, an add command located at memory address 01. Which 2 registers will the CPU use right now to start that fetch? The cycle simply repeats. The program counter holds the address 01 and sends it directly to the memory address register to pull the new data from RAM. Now the arithmetic logic unit, or ALU, can execute that add command. This is our mathematical funnel. The value already sitting in our accumulator drops into the left side. The freshly fetched operand drops into the right. The ALU combines them, and the new total overwrites the old one. Notice the distinct roles here. The ALU is the physical calculator, performing the math, but the accumulator is just the clipboard. It holds the final answer until we need it again. Executing an instruction is not a complex mystery. It is simply the act of routing electrical values through highly specialized physical funnels to change their state. Our original math problem, x equals x plus 1, is solved, but the operation isn't finished. That new value is sitting in a temporary workspace, and it needs to be saved to permanent memory. The store instruction runs the entire flow in reverse. The updated answer in the accumulator moves up to the memory data register. The target destination address drops into the memory address register, and the final value is pushed out across the grid, safely into RAM. Not all instructions manipulate data like this. Some dictate control flow. If this program were a continuous loop, the final command wouldn't store a number. It would simply overwrite the program counter with a new address, forcing the entire system back to the beginning. This cyclical flowchart maps out the universal cheat sheet for modern computing. Every operation runs through these exact 3 nodes. The system fetches the data by routing addresses to RAM, decodes the instruction to find the right physical pathways, and executes the math. The next time you hit run on a complex piece of software, you know exactly what is happening beneath the surface. It is this precise mechanical dance, repeating billions of times a second.